Okay, so the title of the talk is Integrated Planning and Acting with Operational Models. And as motivation, I would like to start with this photo here of Bremen Harbor. It's one of the most important European ports for transporting cars. It's about 400,000 square meters, has 120,000 storage places, and a dozen different technical treatment stations for cars. Each year, about 6 million cars come through the port of 18 different brands. About 8 or 10 years ago, a research group at FBK in Italy produced a prototype system for automated control of the harbor. And here's a rough block diagram of a part of it. I'd like to point out several things that are salient. One is there are multiple levels of abstraction. These correspond to the physical and managerial organization of the harbor. At the higher levels, we have planning of abstract tasks, things like unloading, unpacking, so forth. These are things that can sort of be planned in advance. As we get into the lower levels, we have situations where there are multiple agents interacting with each other and partial observability, because each of these agents can only see its own local environment, and dynamic change as things come into the harbor and things go on in the harbor. So because of that, it's impossible at this level to plan everything in advance. The plans then are abstract and partial until more detail is needed in order to carry them out. Here's another example of a hypothetical worker robot, and it's responding to user requests. Again, we have multiple levels of abstraction with planning at the higher levels. At the lower levels, there's non-determinism, partial observability, dynamic change. And so again, the plans are abstract up here and more detail gets developed as needed down here. In both of these cases, there's an interaction that goes on between planning and acting. Here is a diagram of an actor, and I think Malik put this diagram together, the original version of it. There's an acting component and a planning component. The planning consists of prediction plus search. You're searching some space of states over predicted states, possible organizations of tasks and actions. And for that, it's a large space. You need to evaluate the actions very quickly. So use descriptive models written in languages such as PDDL that predict what the actions will do, but do not include instructions for how to perform those actions. The acting component involves performing the actions. And as I was saying earlier, it tends to be done in environments that are dynamic, unpredictable, partially observable. And so the actor needs to adapt to the current context, react to any events that are occurring. And acting typically uses operational models, which are instructions telling how to perform the actions and whatever complicated situation the actor has to be in. These operational models will then generate commands that get sent to the actor's execution platform, where it will do things that affect the external world and get back signals which are transformed into percepts, which inform the acting and the planning. So as an example of why it's necessary to have both the planning and the acting component, and in particular, why the acting component is important. Suppose we go back to that worker robot again and take this subtask down here of opening a door. Well, how are we going to open a door? It's something that we probably consider to be very easy, but let's think about it in more detail. There's different methods that you need to use depending on what kind of door it is. Is it one that slides? Is it one that is hinged? Well, if it is hinged, then is it hinged on the left or on the right? If it is hinged, say, on the right, well, does it open towards you or away from you? Okay, well, what kind of place do you grasp the door with? Is it a knob? Is it a lever? Is it a push bar? Is it a pull handle? Is it a push plate? Or is it a fish? I guess I can't hear whether people are laughing or not. I hope they appreciated that joke. Okay, what we'll be talking about today are a particular actor, Ray, and a particular planner, UPOM, which operate together. They are implemented in Python. There is a full implementation of them here, and I think Sunandita is putting a link to that on the chat where you can copy it and go to it if you want. And we also have several links to related publications, which you can access when the talk is posted later. So as an outline of the rest of the talk, well, I've just gone through the motivation. The next topic will be the representation that Ray and UPOM use, which involves state variables, commands, tasks, and refinement methods. So in the representation, there are a collection of symbols called objects. They represent whatever objects there are in the domain that you are working in. In this case, robots, containers, C1 and C2, locations, loc 0, loc 1, so forth. There are rigid relations. These are properties that won't change. Location 1 is adjacent, to location 1 is adjacent to location 0. It's also adjacent to location 2, which is also adjacent to location 3, and so forth. So here are all of the adjacency relations. To represent properties that can change, we use state variables. These also have been called fluents in the AI planning literature. And they have some parameters in them. R is a variable denoting a robot. C is a variable denoting a container. L is a variable denoting a location. So location of R, where R is a robot, would be one of these 5 locations. Cargo of the robot would be if it's containing if it's carrying a container, it would be the name of the container. Otherwise, it would be nil. Or actually, I think what we used was empty rather than nil. So I will correct that right now. Position of a container, it could be a location, or it could be a robot, but also it could be unknown because these robots only have local sensing capability. They can only see what's at their current location. View of a location is going to be true or false depending on whether one of the robots has looked at that location. And if view of that location is true, we're assuming that the world is static. So in that case, the position of the container is L for every container C that is at location L. The robots have commands to the execution platform, or excuse me, the actor, which controls both of these robots, has command to its execution platform, which is the robots. A robot could take an object at a particular location. It could put an object down at a particular location. It could perceive what objects are at the location, or it could move to an adjacent location. If you have any questions about any of this, by the way, please ask them. Sunandita is monitoring the chat, and if there's something that is confusing you that you need to be answered, she will call it to my attention. Okay, a task is an activity for the actor to perform, and it is going to have a name, and it is going to have a list of arguments. For each task, there are one or more refinement methods, and these are operational models, instructions telling how to perform the task. So the format we're going to use for these operational models is a name for the refinement method, a list of arguments to the refinement method, which are in general going to include all of these arguments plus possibly some more. The task slot is going to be a task identifier. It's going to say what task name with what arguments this method is to be used for. Precondition is a test telling what things need to be true in the current state in order for the method to be applicable. And finally, the body is a computer program, a special kind of computer program because it includes in it commands that get sent to the execution platform, as well as tasks which would be solved using other refinement methods. So here we have an example of one of these methods. Its name is mfetch. Excuse me, I did not mean to move it. I meant to highlight part of it. It's good for the task of a robot fetching a particular container. In the case where the container is unknown, we have a different method for the case where the position of the container is known. If it is unknown, then the body of this method is this program. If there's a location that we haven't viewed yet, then move there, see what's at that location. If the position of the container is that location, then take it. Otherwise, we recursively call the fetch task, which means that we're either going to do this or this in order to handle that fetch task. Okay? So that's a rough idea of what the tasks look like and the methods. The next item in the outline is to talk about Ray, which uses these things. This is the actor. Excuse me, I did not mean to do that. Ray stands for Refinement Acting Engine. It is the part of the acting component that interacts directly with the execution platform. It typically will have a number of different tasks that it is trying to accomplish. It performs multiple tasks in parallel with each other. It does this purely reactively. There's no look ahead built into Ray itself. For each task, or it can also have methods to handle events. For each task or event, it's going to have a refinement stack. This is basically an execution stack. Remember, we have a computer program that we're executing, so it's the execution stack for that program. It corresponds to the current path in Ray's search tree for the task that it's trying to work on. And I'll give you an example of that in a few minutes. Ray's agenda is going to be the set of all of the current refinement stacks that it has. So if it has a refinement stack for task 1, another one for task 2, another one for task 3, then the agenda would consist of these 3 refinement stacks. The procedure that Ray goes through is a loop where basically it advances each of these things in parallel. First, it looks to see if any new tasks or events have come in that it needs to respond to. Has anything come in here? If a new task has come in or a new event, it chooses a method instance to use for it, creates a refinement stack for that task or event with that method, adds the stack to its agenda, and then for each stack in the agenda, it progresses it by 1 step. So it's progressing all of these things concurrently. And if that stack is finished, then it removes it from the agenda. I will give you an example of that shortly. Any questions so far? All right. Representation. Remember, I went through this a few minutes ago. I'm going to be using this environment here with these objects, these relations, these state variables, and these commands as a running example that we're going to run Ray on. So let's see how we do that. Here is our environment, and we're assuming at the outset that the locations of these containers are unknown. We can see them, but the 2 robots cannot. They can only see what's at their current location. So this is partially observable environment. Ray goes through its loop. It looks to see if there are any external tasks or events that have come in. Well, here's one that's come in. Use some robot, R0, to fetch the container C2. So C2, we know which container it is. R0 is a free variable. We don't care which robot we use. Use some robot to fetch it. Okay, so that's the task. We need to choose a method instance to use for that task. Well, we have 2 methods over here. So let's see which of them we can use. This one could be used because the position of the container is not known. This one is not applicable because it only works when the position of the container is known. So we have a couple of instances of this method of this method that we can use. One instance is use robot 1. Another one is use robot 2. All right? So we choose one of these method instances. Let's choose the first one. So R0 gets bound to R1. And we're going to use these variable bindings in executing the method over here. We create a refinement stack. I'm not showing the stack explicitly. You don't need to see it explicitly because basically it corresponds to whatever the current path is through this search tree. All right? We create the refinement stack and we add it to the agenda. Well, the agenda is going to be simple in this case. We're only going to have one refinement stack in it, so you don't need to worry about what the agenda is. So for each stack in the agenda, and this is the only one, we progress it. Okay, let's progress it. Well, what does the progress procedure look like? Well, there's a complicated piece of pseudocode for it that's written up in some of our papers, but basically it is a decision tree that looks like this. And I won't go through all of the details of the decision tree just yet, because I probably would confuse you. But what I will do is, as we call the progress thing, I will show you how we trace paths through the decision tree in order to figure out what to do. All right? Any questions about any of this? Okay. Here we've called progress with this task and this method instance, and the preconditions of the method instance are satisfied, so we start executing the body of the method instance. So the first statement in here is part of the control structure of the program. Does there exist a location L that we haven't viewed yet? Well, there's a bunch of locations we haven't viewed yet, so let's go to one of them. So the first thing that is a command or a task that we need to handle is the robot needs to move to that location. So let's say that we're using R, well, we know that we're using R1. R is bound to R1 up here. L we could choose to be at location 1. So we have the task of moving robot 1 to location 1. How does all of that happen in the progress thing? Well, it says, have we started executing this method? No. Are there more steps in it? Yes. If so, let tau prime be the next step of that method. Well, the next step is the one that we get to when we follow what this control structure says to go to. That is this thing here. That's how we got here. All right? So next, we look at the type of that step. Is it an assignment or a task or a command? Well, in this case, it's a command. I said it was a task earlier, I misremembered. It's a command that we can send directly to the execution platform. So we do that, and at this point, this call to the progress procedure is done. It returns, okay? Well, what does it return to? It returns to Ray, which was going around in a loop, progressing each stack in the agenda. Well, there's only one stack in the agenda, so it calls progress on that same stack again. So we immediately call progress again. The stack consists of where we are in the search tree. So we sent this command to the execution platform. It was a command. We look at the command status. Well, it's still running. The robot is moving. It hasn't gotten to the other location yet. So it's still running. So at this point, the progress procedure returns again. Well, it returns to that same piece of code in Ray. Ray calls progress again. It checks the command status again. This time, the robot has finished moving. So the command status is we've succeeded. Are there more steps in M? Well, yes. Here's the next one. So we go to the next one over here. And that means we go to this. All right? We want to perceive what's at location 1. So we send that command to the execution platform. And now suppose that when we send it to the execution platform, what we find out is that this robot's sensors are not working. So we have a sensor failure. Well, at that point, our body of this method instance has failed. That means the entire method instance has failed. We have to abort its execution. If we can't use this method instance for this task, then what the progress procedure says is to retry this same task using an untried candidate. Well, what's an untried candidate? Well, remember we had 2 candidates that we tried or had available for fetching C2. The other one was to use robot 2 to fetch C2. So we invoke that. Basically, we've taken this thing out of the search tree. We're putting this in as its replacement. So our refinement stack now contains this task with this method instance. All right, we're going to use that robot instead. So I have a question for you. Is this the same as a backtracking search? When I was preparing this lecture, I was originally thinking that I could ask you to vote on whether this is or not, but I decided later that you probably wouldn't think that that was a good idea. So I'm going to go ahead and answer the question for you. This is similar to a backtracking search because what we have done is we've tried this thing, it failed, we backtracked from it, and we're trying this thing instead. But it is not identical to a backtracking search. In a backtracking search, if you're running a planner in a search space, what happens is that when you backtrack, you're backtracking to the state that you were in before you executed any of this stuff because you're not using that method anymore, okay? Well, we're not in a planner, we're in an actor. It has already sent this command to the execution platform. It has already changed what the current state of the world is. We can't backtrack to that previous state without a lot of overhead of moving the robot back. We don't want to move the robot back, we don't need to. We can just start using robot 2, all right? So this isn't the same as a backtracking search because we are doing it in a different state of the world. I hope you understand the distinction. Any questions about that? Okay, there are several extensions to Ray, which are written up in some of the papers. In view of the amount of time that we have, I'm going to skip all of those. You can read about them in the papers if you're interested. The next point in the outline then is planning. And our planner is called UPOM, which is UCT-like Planner for Operational Models. Some of you know what UCT is. I'll get to that shortly. Well, why do we do planning? Go back and look at the Ray procedure. There's a point where it chooses a method instance out of a set of candidates. There are several points in the progress procedure where it chooses a method instance out of a set of candidates. If it chooses the wrong one, that could lead to a more costly solution, like what we had up here. We started out a robot that had a bad sensor. We wasted some time and energy doing that and had to backtrack and try a different robot. In other cases, it could lead to a failure where we can't just do something else in the current state. We need to invoke some recovery procedure to recover from a mess that we've made. In other cases, it could lead to a failure that we can't recover from at all. So the idea here of doing the planning is to do some simulations to predict what the outcomes of our commands will be. So our planner, we had originally thought of using a typical classical backtracking search operating in a deterministic environment. The problem is that that doesn't work so well in an environment like this. The typical assumptions of classical planning include, among other things, that the environment is fully observable, which this is not. It also includes an assumption that there are no exogenous events. Well, things could happen in this environment. It includes an assumption that there's no non-determinism. Well, in this environment, things can go wrong unexpectedly. So none of those assumptions hold. In order to deal with non-determinism, partial observability, exogenous events, what we're instead going to do is repeated Monte Carlo rollouts. And in each Monte Carlo rollout, we're going to run a simulation where it'll deal with the non-determinism within the simulation. So when we choose a method instance in the planner, this is a tentative choice. We're going to run a simulation of the progress procedure on that method instance. So instead of sending the thing to the execution platform, like progress did, we're going to start a simulation of it on a simulated version of the execution platform. And later on, when we check what the status of it is on the execution platform, rather than checking the command status, we're going to check the status of the simulation. Okay? So that's basically the difference that happens here. Well, I talked about doing Monte Carlo rollouts. Sorry, I'm getting ahead of myself. I first need to talk about the simulation. In the simplest case, that simulation could be the kinds of probabilistic actions that you might use, say, in a typical MDP representation, where you have an action with preconditions that have probabilistic outcomes. If you don't want to do anything more detailed, you can do that, and it may be good enough, where you choose each outcome randomly with whatever probability you have assigned to it, and use this to update the current state. More generally, what you could do would be arbitrary computations. For example, a physics-based simulation of something, where you run the code in this simulation in order to get the prediction of the effects, and the non-determinism and such is built into the way the simulation works. All right, so Monte Carlo rollouts, where do we do them? Let me back up a minute. What happens here is we do a loop. What we're doing, I got ahead of myself, we're doing Monte Carlo rolls on a single task. Our agenda could include multiple tasks for looking at one of them in isolation. So we are choosing a method instance for it, and we are simulating that method instance step by step until the end, all right? And so non-deterministic outcomes can occur in that simulation. We are then running multiple simulations on it. So our planner, UPOM look ahead, is the actual planner that makes use of this thing. It calls UPOM multiple times, comes up with estimates of the utilities of the various methods that it has tried on all of its multiple tries, and returns the one that has the highest average utility. Okay? So each Monte Carlo rollout consists of running a particular method instance all the way to the end. Well, let me give you a little bit of background on, on Monte Carlo rollouts. At each state, we're going to choose, this is not what we do. This is what Monte Carlo rollouts were set up to do on ordinary Markov decision processes. You have states, you have a possible choice of actions. At each state, you choose an action at random, you get a random outcome. There's a well-known algorithm called UCT, which stands for upper confidence bound on trees. And what it does is when it makes these random choices of action, the choices that it makes balance a particular statistical formula that balances exploration of actions that you don't know much about in hopes that you can find out more about them, and maybe they'll work better than what you've seen already, with exploitation of actions that you have tried already that you know work well. So you have a statistical formula which tries to find an optimal balance between those two things. And it can be proved theoretically that if you run this algorithm doing enough of these rollouts, that it will converge at the root of the search tree to whatever the optimal choice of action is up here. So we're doing something like that on UPOM's search tree. Well, its search tree is more complicated because we have tasks, we have method instances. So we have here our disjunction among alternative choices, similar to what we have with alternative actions here, but we're doing it over the methods. When we start executing a particular method, it will give us commands, things that correspond to actions, but we don't really have a choice here because it's dictated by the sequence of code execution. The action may have multiple possible outcomes. We sample from those to get the possible results, and we follow the execution. So we have 3 different kinds of nodes that are traversed in a more complicated way. However, it's possible to prove that if you ignore the possibility of exogenous events, that you can map this search space into a UCT search space on a more complicated MDP than this one. And you can get a proof of convergence to optimal for this thing. So in that case, UPOM will converge to the optimal choice. Any questions about any of that? All right, next thing in the outline, how do we integrate acting with planning? Well, we combine Ray with UPOM. Remember, I said earlier that when we choose a method instance, if we make a wrong choice, that's where we can get into trouble. And that can occur here. It can occur here, or here, or here. So what we're going to do is whenever Ray needs to choose a method instance, it's going to use UPOM lookahead to make the choice. So UPOM lookahead will do some simulations of the method instances that are available and choose the one that has the highest estimated expected utility based on however many rollouts it has done. There is a paper that we have that is going to be presented at the ICAPS conference very soon, where, among other things, we did some experiments involving Ray and UPOM on a number of different domains. I won't get into the details of these domains, except to say that all of them included dynamic events. Most of them included dead ends where you reached a failure you couldn't recover from. Most of them included sensing. Most of them included collaboration among multiple robots, and all of them included concurrent tasks. Along a number of different evaluation criteria, our results were that planning helps the actor do better. Ray operates better with UPOM than it does without it. And it operates better if you do more Monte Carlo rollouts so that you get more informed planning than it does if you do fewer Monte Carlo rollouts. Okay. There are some other details of Ray and UPOM. Again, I'm going to skip those in the interest of time. At this point, I'm done with my part of the lecture. For the next part of the lecture, Sunandita is going to talk about using the implementation of Ray and UPOM. So she's going to show you the Ray code and the UPOM code, run it on some examples, and we'll give you a chance to run it yourself on a server where she has set it up for you to run. Before she does that, however, I'd like to open the floor for discussion and questions about anything I have discussed so far. Have any questions come up?
So there is one question.
Yes.
So does Ray handle the temporal constraints, and do we have to do anything like that in future? Can it handle them, like, can Ray handle it implicitly or explicitly?
I have 2 answers for that. One of them is yes, the other one is no. Both of them are partially correct. Ray can handle temporal things in the sense that, remember, when we go back to, let me go back to simulating. When it simulates it, this simulation is going to include things like how much time is this simulation going to take. And so it would be trivial as part of that simulation to update a timestamp that you can keep in your current state that tells you how much time has occurred. And so you can do some elementary reasoning about time there. However, it doesn't really handle temporal constraints in a full-fledged way. Part of the reason is, remember, when we run UPOM to do this simulation, it is only doing it for a single task in isolation from all of the other refinement stacks that it has in the agenda. So it's not really looking at interactions among the multiple tasks that it is trying to accomplish. And consequently, one of the things that we found in some of these experiments were situations where UPOM didn't really do as well as it could have because it wasn't looking at ways in which some of the tasks interfered with some of the other tasks. We are doing some work on that. Part of that is occurring in the context of a multi-agent version of Ray and UPOM that another of my students will be presenting at the DMAP workshop next week, which is associated with ICAPS. And there we have multiple agents, each running versions of Ray and UPOM interacting with each other. So he's having to handle time a little bit better than we're doing here. There's still more work, however, that needs to be done on that, and that is definitely a topic for future work. Sorry, that was a very long-winded answer to a simple question. Do you have any other questions?
Yeah, so there is a request for going through the refinement tree again.
Certainly.
Like the UPOM's refinement tree.
UPOM's refinement tree. So that would be where we are calling UPOM in order to simulate a method instance. Is that correct?
Yeah, I think it's slide 39.
39, okay. Yeah. Here.
Yeah.
All right. Well, this is an abstract version of the refinement tree. So I didn't intend to get into the details of that. That's part of the reason why it's confusing, I imagine. Let me try to relate it a little bit better to what's going on here, all right? Or excuse me, let me relate it a little bit better to something like this method execution here, all right? In order to do that, let me take a copy of that method and drop it down here where I can refer to it, all right? So if we're executing something like this, or an instance of something like this, I should say, well, we have a task. We have a disjunction among alternative method instances. So a method instance would be something like this with a particular binding of the variables. And I gave you an example of that with R1 and C2 here earlier. Sequence of code execution for that method, that is basically we're doing our simulated execution of the body of the method, okay? So that can have loops in it, it can have if then else tests in it, it can have all of the things that occur in computer code, but also it can have commands and it can have tasks. Commands would get simulated, tasks would be handled by choosing other method instances for them. So here's a command. We run a simulation of it. We get a possible result. From that possible result, that gives us the current state of the world, simulated state of the world, that we then use as input when we are trying to handle this task. And that can influence which method instances are applicable. There's then a big piece of the search tree, which I didn't include down here, where we have other choices, other code execution, other commands, other tasks, so on. Once we've finished with that, we come up here, go to this command, and so forth. Once we have finished with that code execution, we come back over up to here. What all of that has done is it's completed one Monte Carlo rollout. So on the one hand, all of that sounds rather complicated. You might be wondering, how can UPOM look ahead do a reasonable number of these in order to do simulations in real time in order to inform an actor? Well, part of the way that that happens is one of the things that these methods accomplish. If you're looking at various methods for accomplishing a task, you are avoiding looking at a whole bunch of actions that might be irrelevant for accomplishing the task, but are nevertheless applicable in the current state. So you're searching a much smaller search space than a classical planner might search. And that can help with it. And in fact, in the experiments, as I indicated, the planner did do well. All right? Does that help?
Yes, he understands.
Okay, good. Any other questions?
Another question is how MC simulations help dealing with partial observability?
Oh, how do they help? Okay, well, hold on a second. If you're running a simulation, one of the things that you would simulate if you were in a situation like this one, where you are searching for the container. One of the things it would simulate would be whether you see the container at this particular location or not, all right? Well, the way the partial observability would work in that case, you might have an a priori probability that the container will be at that location, and that would enter into the simulation. And if you sample over that probability distribution, on some of your Monte Carlo rollouts, the container would be there. On some of the others, it would not be there. On the ones where it is there, your simulation would then simulate whether the robot is sensing the presence of the container or not. And so if you know, for example, this particular robot has a bad sensor, you can simulate the sensor failure. Does that answer the question?
Yeah.
Okay. Any other questions?
No.
Okay. Well, thank you very much then. And I guess we are ready for Sunandita's part of the lecture. She's going to start out with the code demo. Sunandita, please go ahead.
Yeah, so for running the code, I would prefer that you use Unix-based operating system, because in Windows there can be some errors. I have not tested the code on Windows like thoroughly. And you can have like the Docker or the Python Conda environment pre-installs. The code doesn't depend on several packages, but something basic that comes with Conda. So the things that you can modify are the domain files, which will decide the tasks, refinement methods, and the commands, and the problem file, which will decide the task and its parameters and the initial state that Ray starts with. And the domains, so in our implementation, we have 5 simulated domains, and I have also created a simple domain file so that you can modify it and see like what is happening. That is called test. So yeah, let me share my screen now.
Okay.
Dana, can you stop sharing? Yeah.
Yes, I just did.
Okay. Is my screen visible?
Yes.
Okay. Because it's not showing the Zoom's border, so I was confused.
Oh, okay.
So yeah, I'll show the steps for Conda. If you have any doubts about the Docker steps, we can discuss it on Slack, or you can also email me about it. So first, you have to create the Conda environment. Using the ray.yml file. So I had already created this before, so I'm getting this error, but for you, the environment will be created. And then you have to Conda activate ray. So here you can see on the left, you have the ray environment now. Then you go to the folder Ray. Oh, sorry. Go inside Ray and UPOM, and then run Python 3 test Ray and UPOM. To look at the list of parameters, just do -h. So yeah, for help, you just to get this message, the command is -h. And there are different options for the verbosity, like how much output do you want to see. If you don't want to see any outputs, just the results, then just use this parameter as 0. If you want to see some outputs, then 1. And if you want to see like a lot of outputs, then 2. The domains, so each domain has a code. So these are the set of codes that you can use. Problem, like I'll show each of the domain file and one of the problem files, and you select that which problem you want to use. Then which planner, you can use no planner, then it's none, or the planner can be UPOM. Depth is the maximum search depth, like till how deep the UPOM will explore the rollout. And if the rollout seems to continue after that, then at this depth, UPOM will estimate the remaining utility using a heuristic function. Then what is the time limit for running Ray? Then the number of rollouts in UPOM, that is NRO, and which utility function you want UPOM to optimize. So there are two options, efficiency or success ratio. And there is a way to define your own utility function as well. And do you want UPOM to do iterative deepening? So in iterative deepening, what happens is the rollouts are explored in depths of increment 5, because we have this feature because UPOM is being used online. So you want the flexibility of making it as fast as possible. Now let us run one simple problem. Say the domain is chargeable robot, CR, and the problem is problem 5. So it ran very fast. The results is the task identifier fetch, and it has two parameters, R1, and it has to fetch object O1. The result is that it succeeded, and retry count is 0, efficiency is 0.08. Another task was this event emergency. So at location 2, there is emergency event 1, and the result is that it failed. That means the robot failed to handle the emergency. Then let us test with a different verbosity level, say V1. Then you have some more outputs. So say Ray receives this task, fetch R101, then it has to plan for this task. So it is calling the planner UPOM. UPOM ran and returned fetch method 1 for performing task fetch. And then Ray starts executing the method fetch method 1. Inside the fetch method 1, it has task move to. But since move to has only one refinement method, it will just execute that instead of planning. By this time, Ray has received another task, emergency, and it creates another stack 2 for this task. And since the progress works in like a round robin manner, it is doing one step of each task at a time. So again, we are back to something related to stack 1, which is executing move to method 1. And then inside move to method 1, there is like a non-emergency move task. And for that, again, there is another method. So this is like a detailed view of which methods and commands are being executed and how it's like, what is the result of that. Okay, now let us look at a simple domain file and a problem file. Yeah, so the domain files can be found inside the folder domains. So so this is the chargeable robot domain that I just ran an example of. It has several functions. This is the description of the command. You can define any control logic, any programming procedure inside here in Python. After the commands, you have the set of refinement methods. So recharge is a task and it has different methods for it. Search has different methods. Then after you define all the tasks and methods, you declare the commands. So just put them in a list, the functions that you have defined for commands, and just use this alg. So alg is imported as, so ray1 and upom is imported as alg. Then you declare each task and the parameters that it has. So search has the parameters robot and the object. Fetch has the parameters the robot and the object. Recharge are a robot and the charger, and so on. Then you have the methods for each task. So search has two methods, search method 1, search method 2. Fetch has two methods, fetch method 1 and fetch method 2, and so on. Then you define the heuristic functions. Like if you run upom with limited depth, then you need the heuristic. So this is one very simple heuristic, which is like estimates that you don't need to do anything because the efficiency is infinite. So that means the cost, which is the reciprocal of the efficiency, is 0. And you have another heuristic functions that depends on the charge of the robot. Another thing that you need to define is the environment in which the robots or the agent will be operating in, which is the environment file. So in our implementation for the simulation of commands, we just sample the outcome from a probabilistic distribution. So take has a chance of succeeding 90% and failing 1%. Put has a probability of succeeding 99% and failing 1% of the time, and so on. And when you sense, so if say you have a perceive action and you are doing a simulation of it, you don't know that where the objects are and so on. So for that, what we do is we have a sense objects that samples uniformly from all the locations. Like all the locations have equal probabilities of having the objects, and we just sample one of them. And for similarly, for each command, you can have your own simulation defined here. Also, if you have like a more sophisticated simulator, then you have a way of plugging that in as well. So if you want to do that, then you have to plug it in the simulate function, which is in the GUI file. So whichever simulator you want to call, you have to call here. So what I've done here is I've just created a mock output file, which prints in the host directory. So for the task that we just ran, the robot moved from location 2 to 8, and the robot is at location 2. Then it picked up object 01, and then it failed to address emergency 1. Now let us look at a very simple domain and like change its parameters and see what happens. So this is one very simple function, a simple command fail, which always returns failure. Then there is a simple command C1, which just simulates that you're doing C1, and it senses the results of C1. So for this domain test, there is a simple environment file. So C1 succeeds with probability 0.8 and fails with probability 0.2, C2 with 0.5, 0.5, and C3 0.9 and 0.1. And a simple, let's go back to the domain file again. Yeah, so you have three commands, C1, C2, and C3, and a refinement method T1, M1, which will calculate this value, C, or you can call it something else also, D maybe, and simulate D. like you can put any code inside this. We'll change this and see what happens as well. Then do command C1, do command C3. Similarly, there is another refinement method, T1 M2 for task T1, where you do commands C2 and C3. Then you declare all the commands, C1, C2, C3, and fail. Declare the task T1 and its parameters, A and B. And declare the methods for T1, which is T1 M1 and T1 M2. Then you have the heuristic, which is infinity. And you declare the heuristic, that heuristic 1 is the heuristic for task T1. Now let us go back to the terminal and run this for the test domain. Sorry, I think I forgot to discuss the problem file. Yeah, let's go look at that also. Yeah. Yeah, so in the problem file, you define the duration, which is basically the cost. I thought like I use this term duration because in the beginning I was thinking about time, but it can represent any cost. So the costs are defined as for C1 as 5, C2 as 2, and C3 as 10. So there are two things, because Ray can be run in the counter mode to make the test run faster, but you can do it in real time as well, but it will run slower. So reset state is the initial state, which has a state variable called val, and for current it's 1. And the tasks arriving are at time 5, you have T1 with parameter 5 and 10, and at time 6 you have T1 with parameters 1 and 3. So now let's run the task, run this task, or run this problem. So yeah, so the result is that T1 has succeeded, and there were no retries in this, but T1 1 and 3 succeeded, but T1 5 and 10 failed. So what is the reason for this failure? Is probably because okay, so let's look at this with more verbosity. Then if it fails, we'll be able to understand why it fails. Okay, so this time it succeeded, but still let's look at the explanation for it. Like first you have this task T1, 5 with parameters 5 and 10. It calls the planner, and the planner returns this refinement method T1 M2, which is 5 with 5 and 10. And then you try this T1 M2 method. For T1 M2, you start to execute the command C2. And then by this time, there is another task that has arrived for Ray, that is T1 with parameters 1 and 3. So this task is beginning in the stack 2. So each task has a new stack for itself. And the commands are being executed in the stacks. Like this first item is the, in this notation, is the first item is the stack ID, which is 1 and 2. And the second one is what is the depth inside this stack. Similarly, for the task T1 for the task T1 with parameters 1 and 3, it has the planner UPOM has suggested the method T1 M2, and again it is executing the method. Now let's look at the output file, which is inside the host directory. So here it says that what the actor is doing. So first is doing C2, then C3, then C2, then again C3. Now let's look at how we can set the different parameters. Say if you want to optimize a different utility function, so you can set that. Like by default, it optimizes the efficiency, but you can set it to success ratio as well. And you can also set the number of rollouts, which is n arrow. If you you can set it to even 1 and see what happens. So if you do it 1, you see that the result is success and the efficiency is 0.08, and here again result is success with the efficiency 0.08. Let's do it with more rollouts and see. But I think this was like by chance it happened. It may fail as well. Like let's see and get failure. Okay, this succeeded again. That's strange. Like it's very lucky today. Then let's look at more number of rollouts. Again, it is succeeding. And you can also optimize the efficiency. So here the efficiency is 0.08, and for the second one, it's 0.02. Let's look at some other parameters. So yeah, you can also run it in purely reactive mode if you set the planner to none. So yeah, if there's no planning, then this one failed. And if a task fails, then the efficiency of it is 0. And the planner can also be UPOM, which is the default choice. So in this case, both succeeded. Let's try with do iterative deepening as well. Yeah, because it's iterative deepening, so it is taking a bit more time because it is looking at till the maximum depth in steps of 5. Now let us make some changes to the domain file and see what's happening. So inside the refinement method, T1M1, you can check that if say A, let us look at the value of A here. A is 5. So what we can do is we can say that, okay, if A is less than 5 or A is greater than equal to 5, then alg.do command C1, otherwise do C2. So this is for when you choose this method T1M1, and for T1M2, if let's do it like it always fails. So this will never succeed. And see what happens. Oh, there is some indentation issue. Yeah, so in this case, T1 failed, and okay, let's see which method is being chosen. Yeah, T1 M1. So planner is returning T1 M1 because T1 M2 is always failing. Now let's see that what happens if we make T1 M1 always fail and T1 M2, we remove this fail command from here. Yeah, then it's returning, the planner is returning T1 M2. So yeah, you can try modifying all these commands and methods and see like how the code is behaving. So one thing you can play with is the parameters here in the command line. And another thing you can look at is the output in the host directory. So it will say that which commands are being executed on the execution platform. Okay, yeah, so I'm done with the demo. Does anyone have any questions?
So I think the last question there in the chat you might have answered already, but how does running MC simulations help with dealing partial observability? Was that from before?
Yeah, I think Dana already answered it.
Great. So
I don't see any new questions.
I
Okay.
have
But it
one.
says, Sunandita, when you say results in your demo, is that this is a result of a simulation at the acting level, which is different from the simulation
Right.
performed by the planner.
Yeah.
Yeah, that Dana explained.
Mm-hmm.
There are two levels of simulations here. I'm not sure this was clear to everyone.
Yeah, so the reason it might not be clear is because in our experiments, we use the same probabilistic model for acting and planning, but that's not necessarily true for like all domains. Like you can have domains where the actor uses a execution platform and the planner uses a simulator to simulate the commands. So if you want to plug in a different simulator for the actor and planner, the place to do it will be in this simulate function. So if you check that whether it's in acting or planning mode and then do the commands accordingly.
Okay, that was exactly my question.
Okay.
Thank you.
I have a question.
Mm-hmm.
So when you showed the refinement method examples, I did not see a precondition formula for any of them, which in this case means that they're applicable regardless of the current state. If you want to have such a formula, how do you do it?
Yes, right. Good question. So for that, say this is the method where you want to have preconditions. Then what you have to do is below the method, you say that T1 M1 has a member called parameters, which is equal to A B if, so this can be any Python expression that is evaluable. Like if you do the eval of that expression, then it returns something. If A greater than 5, say this is the precondition, something like that.
Any reason why that's called parameters rather than precondition?
So we call it parameters because it can also define the values of parameters that are not instantiated by the task.
Okay.
So it's like the one expression that is used for both preconditions and instantiating parameters.
All right.
Going back to the questions by Salar about partial observability, there was one point where you can have information gathering actions emerging from the plan. Would you like to comment on
that? So for information gathering actions, when you do it on the real world or like the actor's execution platform, then you will get like only one outcome. But to simulate it, in our experiments, what we do is we sample it from like a uniform probability distribution.
Yeah. So I have a question to the two of you. With this viewpoint focused on acting and the actor with operational models using hierarchical refinement of tasks, you end up doing planning through simulation. It's not a generative planner. You do not generate a course of actions. Mm-hmm. You do choose make a good choice among alternative courses that you have in your methods. And then you run into the usual criticism raised for HTN, where you require domain knowledge. And your demo showed some yes, programming in this domain knowledge, because your methods can be any kind of code. Mm-hmm. So how do you intend to face this issue of the requirement on a lot of domain knowledge?
I think that's a real issue. We have a project going with some researchers on cybersecurity, where we are looking at how to use Ray for recovery from attacks on software-defined networks. And for that, they have a human expert who supplied us with some methods, but at some point, the human expert was didn't want to supply any more, and they started asking us about ways to learn the methods automatically. That is something that we are interested in. It is something where we don't have a solution for it yet, but it's our current work in progress.
Okay, so this may lead to the following lecture by Alan Faird, who will tell us about model-based reinforcement learning. Maybe some of the approaches Alan will mention can be helpful to your projects about that. Any additional questions, remarks? Maybe I can add one point regarding the handling of time. The acting part of Ray can easily handle timeouts, synchronization, that are part of the method. And then I go back to the answer you provided, that is through the simulation that you can check that this is met or not met, or this leads to some level of your utility function. I believe that's it. If there are no further questions or remarks from the attendance. Thank you very much, Sunandita. Thank you very much, Dina, for this nice and very well illustrated talk.
Yeah, thank you for giving us the opportunity.
Yes, thanks, Michael and Malik. Goodbye.
Thank you.
Bye.
Bye.